Hey everybody, we are talking acceleration today, the final piece of the motion puzzle. And when we're talking acceleration, we are talking about changes to motion. So how do you change the motion in your car? There's a few ways. You could use the gas pedal to speed up. You could use the brake pedal to slow down, or you could use the steering wheel to turn. And so when we're talking about any of those, whether you're speeding up, slowing down, or turning, those are changes to motion. Those are accelerations. So we say speeding up, slowing down, or turning, changes to speed or direction. And more simply, changes in velocity. That's acceleration. We measure acceleration as a rate of change in velocity. So a rate of change in speed or direction is acceleration. And so again, rate means how fast something occurs. We've been looking at rate of changes in position when we look at velocity. This is a rate of change of velocity. And so more specifically, how much does velocity change per time interval? And just to recap, per means to divide. So that means acceleration is going to be how much the velocity changed divided by the time interval over which it did change. So again, acceleration is equal to how much did the velocity change divided by the time period, the time interval over which that velocity change occurred. All right, so a little more of a recap. We started with position. We measure that in meters, and that is where the object is from its origin. Velocity is the next step. That's the rate of change of position. We measure that as rate, again, is how long. So meters per second. How fast is the object moving towards or away from its origin? And then we're now at acceleration, which is the rate of change of velocity. So rate of change of speed or direction. So that is how fast the object is changing, how fast it moves towards or away from its origin. And I know that seems really overwhelming, hence the shocked Keanu Reeves look right there. So from a formula perspective, from a math perspective, we say that acceleration is equal to the final velocity minus the initial velocity divided by the time interval where the velocity changed, or when the velocity changed. So you take your final velocity, subtract the starting or the initial velocity, and divide that over the time period from when you started to finished. So your change in velocity divided by your change in time. Now the units look a little strange. We're taking a difference in velocity over time, and we know that velocity units are meters per second. Well, you're putting meters per second over seconds, which again looks a little strange. So meters per second per second. Yeah, I know. Take a second, think about what that means. Specifically, what would 5 meters per second mean? And again, we're talking about a change in velocity over time. What that's telling us is that for every second that passes by, the velocity changes by 5 meters per second. So every time a second goes by, the object is changing its velocity by 5 meters per second. So we're going to take a look at some data to hopefully make a little more sense of that. And so in this example, let me kind of give you a rundown of what the table is. This is the initial time, the start of a second. And at the start of that second, this is the initial velocity of the object. The acceleration rate, you'll notice, stays constant. And then we have the final velocity at the end of that second. So for example, our initial time is 0. We're starting at 0. Okay, the initial velocity of the object is 0 meters per second, so it's not moving yet. That object is going to accelerate at 5 meters per second. Okay, so over the course of this second, from 0 to 1 seconds, that time interval of 0 to 1, that object increases its velocity by 5 meters per second. So every second, the object will increase velocity by 5 meters per second. All right, so right now, at the end of this first second, we are going 5 meters per second. Now we start the next second. From 1 to 2 seconds, that time interval, same acceleration, the object is going to change its velocity again by 5 meters per second. And so now at the end of that second, we are now at 10 meters per second. So every second that goes by, velocity increases by 5. That's all that this is telling us. So 5 meters per second means that for every second, velocity is going to change, in this case, by increasing by 5. So let's simplify the units a little bit. We know that acceleration is the change in velocity over time, the time interval that change happened. So meters per second per second. If we were to take the reciprocal of our denominator, reciprocal of second, so we're taking the numerator here and multiplying by the reciprocal of this value, so 1 over seconds. These are equivalent. This formula and this formula here are equivalent. We get a simplified unit of meters per second squared. Okay, so that's typically how we're going to write units of acceleration. We typically use this unit in this class, meters per second squared. It's just a simplified version of meters per second per second. So what does this look like graphically? What does acceleration look like graphically? So here's a scenario, and I want you guys to think about what the position versus time graph and the velocity versus time graph will look like. So we have a car, and at time 0, it has a velocity of 2 meters per second east. At time 1, it has a velocity of 2 meters per second east. At time 2, it has a velocity of 2 meters per second east. And at time 3, it has a velocity of 2 meters per second east. So velocity is always 2 meters per second east. Is it accelerating? We know the position's changing, but is velocity changing? And the answer is no. So let's take a look at a graph, or two graphs really, of this object. We're going to graph them simultaneously so you can see the changes. So position, we start at the origin. Velocity, keep in mind we are starting at 2 meters per second, so we are going to put a 2, or put a point at the y value of 2 for velocity. All right, our next point is at time equals 1 second, and our velocity is still 2 meters per second. So while position is changing, velocity is staying constant. And so we'll plot the other points here. Okay, so you can see that the position versus time graph is sloped. The velocity versus time graph is not sloped. The slope of a position versus time graph gives you velocity. So the slope of this graph is actually the velocity. The slope of this graph is 2 meters per second, and that is our velocity here. And an additional item I want to point out, because we're looking at a velocity versus time graph, velocity versus time graphs give you info in their slope as well. The slope of a velocity versus time graph, or velocity y over time x, is acceleration. The object did not accelerate here, the velocity did not change, and we see that the slope here is 0. All right, so what will the position versus time graph and velocity versus time graph look like for this scenario? So we have the object at time 0 starting at a velocity of 0. At time equals 1 second, so 1 second went by. Velocity is now 2 meters per second east. After 2 seconds, the velocity is 4 meters per second east. And after 3 seconds, the velocity is 6 meters per second east. So now we have a changing velocity. We have acceleration. And so when we graph those points again, we see something interesting happening on the position versus time graph. You can see that it has a curve to it. And because the slope of a position versus time graph is velocity, this has to be curved when velocity changes, because as time goes on, velocity is increasing. The slope is getting steeper. And that's telling us that as time goes on, the object is covering more distance in a shorter amount of time. Our velocity graph now has a slope to it because it is accelerating. Remember, the slope of this graph is acceleration. Velocity is increasing over time. That change in velocity we call acceleration. So acceleration is a vector, and direction of acceleration matters a lot. This is a huge concept that you're going to want to be comfortable with, especially for the next unit when we get into forces. So acceleration in the same direction of motion. If I'm moving rightwards and I'm accelerating rightwards, I am speeding up. Okay, so if acceleration is happening in the same direction as I'm moving, I'm speeding up. If I'm accelerating in the opposite direction of my motion, I'm slowing down. So if I'm braking in my car, I'm actually accelerating backwards. Okay, so moving forwards but accelerating backwards, that's going to slow me down. And acceleration in any other direction, not in the direction of motion, not opposite the direction of motion, but any other direction relative to motion, that would be turning. The object would be turning. Now, it's easy to think, oh, negative acceleration means I'm slowing down, but that's not always the case. If you're in motion in the negative direction in your frame of reference and you are negatively accelerating, you're speeding up because both of those are in the same direction. So be very careful not to assume that negative acceleration means you're slowing down. Always look at the direction of motion and the direction of acceleration to determine if you're speeding up or slowing down. If they're the same, you're speeding up. If they're opposites of each other, you're slowing down. I'm going to put a few practice problems on the screen for you. Feel free to pause because the answers will show up after a few seconds, and if you want to test yourself, you don't want those popping up too soon. Good luck! All right, one last question for you. Of these options, which of these is acceleration? Pushing the gas pedal, pushing the brake pedal, and turning the steering wheel. Which of those is acceleration? The answer, all of them. Okay, really important that you understand that speeding up isn't the only form of acceleration. A change in velocity is acceleration, and velocity can slow down. Or you could turn, you can change direction. Of course, you can speed up. Those are all forms of acceleration. All right, so in summary, when we're looking at motion, we're looking at if it's moving, it's in motion, how far did it go? We talk distance versus displacement. How fast is it going? We can look at the average or the instantaneous speed. Where is it going? Okay, so it's in motion in what direction? We're talking velocity. And finally, is that motion changing at all? That's acceleration. If you have any further questions, please feel free to reach out, get extra help, and hopefully this helped you understand acceleration a little bit better. Thank you for watching. Have a good one.